Chapter 9 is called Gauss elimination, and now we'll look at methods to solve linear systems of equations or system of linear equations. The graphical method, of course, you can draw the system of linear equations. So if you have two equations with two unknowns, then you can draw them wherever they intersect. Then that's the point of our solution. So that's a graphical technique. If you have, for example, a 3 by 3 system, then you can draw the three lines. Of course, in that case you are not going to get lines, but you get planes. So wherever the three planes intersect, that's the solution. After this, it becomes difficult to imagine how you can imagine, let's say, a 4 by 4 system. Graphing, of course, the equations, we can also get an idea about what's happening in the system. If you have two parallel lines, then in this case you are not going to get a solution. So because they are parallel lines, so no solution exists in such a case. In a case like this, where you have two lines overlapping each other, so you have one line which is, let's say, minus half x1 plus x2 equal to 1, and you have the other line which is minus x1 plus 2x2 equal to 2. So both of them are on the same location. Both of them overlap each other. This is when you have an equation of the form a plus b equal to c, and then another one 2a plus 2b equal to 2c. So both of them are overlapping each other. We say infinite solutions exist because they intersect at all points. So you can say all of the points are solutions. In this case, there is no solution because they are parallel lines. They will never intersect. A case like this, we call this an ill-conditioned system, where the lines intersect, but the point of intersection here is not very clear. You cannot really make out at which point they are intersecting. So those lines which intersect but they are very close to each other, almost like this, but they are not really overlapping each other, slightly off, but you cannot really make out a clear distinct point of intersection. We call this an ill-conditioned system. Equations will become difficult to solve. Before we continue, we define what we mean by a determinant of the system. Determinant of the system, usually written by this symbol. If you have matrix A, then the determinant is by this symbol. It does not mean absolute. And when you are talking about matrices, this symbol means determinant of the symbol. So determinants for small matrices, if you have 1 by 1, then the determinant is simply that number. If it is 2 by 2, then it is the product of the main diagonal, of the primary diagonal, minus the product of the other the elements in the other diagonal. If you have a 3 by 3 system, then you take A11, then you cross out elements in that row and column. Whatever is remaining, you take the determinant of that. So A11 multiplied by determinant of A22, A23, A32, A33, minus, then now you are going to select the second element, A12. You cross out the row and the column of that element, and what is remaining is minus A12, A21, A33, A23, A31. So that's the elements remaining. Then plus, you select the element here to get rid of the rows and the columns of that element, and whatever is remaining, a21, a22, a31, a32, you take the determinant of this. It's 1 is plus, then negative, plus. So let's say if you have a 4 by 4, then that will be negative, and so on. The determinant for matrix is larger than 3 by 3 can be very complicated. So let us see, find the determinant of this matrix. So it will be the diagonal, the primary diagonal 3 into 6, minus the other diagonal, which is 5 by 2. Always we start with 1 plus, then 1 will be negative. So it's 18 minus 10. So the answer is 8. So the determinant of this matrix is 8. The determinant of matrix like this, we said we'll select 1. We cancel out the row and column of 1. So 1 multiplied by determinant of 4, 6, 5, 6. That's what's left here. Then you select 7. So we had 1 with plus, then minus. So you select 7, cancel out the row and column. You are left with 3, 6, and 5, 2. So 3, 6, 5, 2. Then you select the last one is 2. So cancel out the column and the row of 2. So plus 2 multiplied by 3 into 6, 4 into 2. So 1 multiplied by 24 minus 30 minus 7, 18 minus 10 plus 2 multiplied by 18 minus 8. So 24 minus 30 is minus 6. 8 minus 18 minus 10 is 8 multiplied by 7. So minus 6 minus 56. 18 minus 8, 10 into 2, 20. So minus 6 minus 56 minus 62 plus 20 minus 42. Yes, determinant of a matrix can be positive, can be negative as well. In MATLAB, we can use the built-in function det to find the determinant. So you define your matrix as a matrix here, and you can use the det function determinant of A, and you get the answer for the determinant. So that is how you use the built-in function det for determinant to find the determinant in MATLAB. A square matrix that is not invertible, it means you cannot find its inverse, is called a singular matrix, or we call it a degenerate matrix. And a square matrix is singular or degenerate if the determinant is 0. If the determinant comes out to be 0, then you cannot find an inverse. And of course this is problematic because you cannot find an inverse. You cannot find an inverse, it means you will not be able to solve this matrix. So 1 into 1 minus 1, so 1 minus 1, that is 0. 3 into 4, 12, minus 2 into 6, 12, that is also 0. Now we have matrix here. We said it's going to come out to be 0. Let's just find the determinant of this, make sure it is 0, and get practice on how to find the determinants. Okay, to find the determinant of this matrix, we start with the first one, so minus 3 multiplied by, we cancel out this column and the row, so we'll be left with 14, 1, 29, minus 2. Then we have minus 5, so minus and minus becomes plus, and we have the determinant of 9, 1, 18, minus 2. Yeah, so we get rid of the middle column, so we'll be left with 9, minus 2, and 1, and 18, plus, not here, plus 1. Now we get rid of the third column and the first row, so we'll be left with 9, 14, 18, 29. So that becomes minus 3 multiplied by 14 into minus 2, which is minus 28, minus 29, plus 5 into 9 into minus 2 is minus 18, minus 18, plus 1 9 into 29. So 9 into 29 means 29 tens are 290 minus 30 plus 1, so 261 minus 18 into 14, so 18 tens are 180, 18 fours are 72, so 18, so 252. Okay, so minus 3 into minus 28 minus 29, so minus 28 minus 56, so minus 57 plus 5 minus 18 minus 18, that's minus 36 plus 1, 261 minus 252, that is 9. Minus 3 into minus 57, so 57, so 63 are 180, so 180 minus 3 into 3, 9, so 171, so minus and minus becomes plus. Minus 180, 36 into 5 is 180 plus 9, so that becomes 171 plus 9 is 180 minus 180, which is 0. So the determinant of this matrix is 0. So we say that this is a singular matrix because its determinant is 0. Now one method that we have for solving systems of linear equation is the Cramer's rule, and Cramer's rule states that each unknown in a system of linear algebraic equations can be expressed as a fraction of two determinants, with denominator d and with the numerator obtained from d by replacing the column of coefficients of the unknown in question by the constants. Let's see what we mean by this. Let's say if you have a system like this, so you'll get your A matrix as coefficients from here, so it will be 0.3, 0.52, 1, 0.51, 1.9, 0.1, 0.3, 0.5, so that's your A matrix. Your B matrix is minus 0.01, 0.67, 0.44. The determinant we call D is the determinant of the A matrix. So you find the determinant of the A matrix. I'm not going to waste time here finding this determinant. You can use the built-in MATLAB function, or you can find it by yourself. This is what it comes out to be. So that's the determinant D. Now you find x1 by finding determinant D1. Determinant D1, you replace the coefficient of x1, which is the first column, by the B matrix or the B vector which you had on the right hand side. So you change this by the B vector, and then you find its determinant. So x1 is d1 over d, so it comes out to be minus 14.9. To find x2, you replace the middle column by the B vector, and then of course this as the original A matrix, only you are changing this. You find the determinant d2, and x2 is d2 over d, that comes out to minus 29. To find x3, you replace the third column by the B vector, and then you find the determinant d3, then x3 is d3 over d, and you find it as 19.8. So that's the Cramer's rule. That's how we use it to find solution of system of linear equations. This is the Cramer's rule in MATLAB. You define your A matrix and your B matrix or vector. D is determinant of A. A1 is the B here, and then A, all the rows, columns 2 to 3, and find determinant D1. A2 is the first column is same as the first column of A, then B, then the third column of A, and you find determinant of A2. Then A3 is A, the first and second columns, and B as the third column, and then you find determinant D3 of this matrix, then x1, x2, x3 of these three, and you get the answers as minus 14.9, minus 29.5, and 19.8, just as we have seen them before. Okay, this is problem 9.4. We have given a system of equations, three unknowns. Says compute the determinant, use Cramer's rule to solve for the x values. Anyway, in the Cramer's rule we are going to find the determinant, so I'll start with making the matrix system. So the matrix system I define the matrix A as a 3 by 3 matrix. It's the coefficients of the system. So x1 is 0, 2, 5, 2, 1, 1, 3, 1, 0. So I'm putting the coefficients of the x1, x2 and x3 here, multiplied by the vector of the unknowns. So we have our unknown vectors here, which is x1, x2 and x3 is equal to the right hand side, which is 1, 1 and 2. Now we find the determinant D as the determinant of the A matrix itself. So determinant of the A matrix, so that's going to be 0 multiplied by 1 into 0, that's 0, minus 1, anyway it's multiplied by 0, so it doesn't matter. So minus 2 multiplied by 2 into 0, that's 0, minus 3, plus 5, so 2 into 1 is 2, minus 3, so that is 0, minus 2 minus 3, 6, minus 2 minus 3 is minus 1 multiplied by 5, so minus 5, so that is 1. So D is 1. Now D1, I'll just copy this, make work easier for me. D1, now I replace the first column by the B column, which is 1, 1, 2. So instead of this, I'll make it 1, 1, 2. So this becomes now 1 multiplied by the numbers I have here, minus 2 multiplied by 1 into 0, that's 0, minus 1 into 1 into 2, so that's 2, plus 5 into 1 into 1 is 1, minus 2. So 1 into 0 minus 1, that's minus 1, so minus 1, minus 2 into minus 2 becomes plus 4, 1 into minus 2 is minus 1, minus 1 into plus 5 is minus 5, so minus 1, minus 5, minus 6, plus 4, that's minus 2. So x1 is D1 over D, that's minus 2 over 1, so x1 is minus 2. So we finished finding x1. In D2 now, I have the same A. Now I replace the second column with the B column, which is 1, 1, 2. So it becomes now 0 into 0 minus 2, minus 1 into 2 into 0, that's 0, minus 1 into 3, so that's 3, plus 5 into 2 into 2 is 4, minus 3. So 0 in whatever you have is 0, minus 1 into minus 3, so That's 0 plus 3 plus 5 into, so that's plus 5, so 0 plus 3 plus 5, that's plus 8. So x2 is d2 over d, so that's 8 over 1, so the answer is 8. D3, I'll start with the original matrix. I replace the last column by 1, 1 and 2, so this becomes 0 multiplied by 2 into 1 is, sorry, 1 into 2 is 2 minus 1, so well, anyway it's multiplied by 0, doesn't matter, minus 2 into 2 is 4, minus 3 into 1 is 3, plus 1, 2 into 1 is 2, 3 into 1 is 3. So the first one of course is multiplied by 0, so that's a 0. 4 minus 3 is 1, multiplied by minus 2 is minus 2, 2 minus 3 is minus 1, multiplied by, this is minus 2 minus 1 minus 3, so x3 is d3 over this, so that's minus 3 over 1, so the answer is minus 3. We can just check our answers. We have minus 2, 8 and minus 3. Let us take the first or the second equation. So 2 into minus 2, that's minus 4, plus 8, so minus 4 plus 8 is plus 4, and minus 3, 4 minus 3 is 1, so yeah, it satisfies the equation. That's our answer for x1, x2 and x3 using the Cramer's rule. Now Cramer's rule is simple and straightforward, but for large systems greater than 3 by 3, then it becomes impractical, because finding the determinant itself is so time consuming. Imagine if you have a 4 by 4 system, then you will have 4 times to find a 3 by 3 system determinant for each determinant. For example, for D you have to find a 3 by 3 determinant 4 times, and we know that a 3 by 3 system you have to find a 2 by 2 system determinant 3 times. So as if you are going to find the 2 by 2 determinant 3 times into 4 times, that's 12 determinants you are going to find for D, then 12 for D1, then 12 for D2, and then 12 for D3, and 12 for D4, so that's 12 into 5, 60 determinants. So such calculations, of course, they take time by hand, and of course if you make error in one of them, then you have got it all wrong. And of course also the computer takes time for such calculations, so we need more efficient systems. One of the system that is used is called the naive Gauss elimination system. We say naive because this is the basic one. There are more modifications, enhancements to the system, to the process. This is called the naive, the basic Gauss elimination system. It has two steps. It has a forward elimination step and then a backward substitution step. We make an augmented matrix of the A matrix and the B matrix. We do the forward elimination by converting it to an upper triangular matrix. We get values in the upper triangle, and the lower triangle of course becomes zeros. So everything below the diagonal is 0. Yes, here in the third row. So everything below the diagonal is 0. Now once we have that, then we start back substitution. Back substitution means, since here you have all zeros, then x3 will be just b3 over a33, whatever you are left with here. Once you know x3, then this equation, you have x2 and x3. Already you know x3, so you can find x2 from here. So x2 will be b2 minus a23 x3 divided by a2, and so on. This is called back substitution. Now how to convert them to zeros? We do row operations, and we can get this to become to zeros. Let us look at how we can do this in the next slide. Okay, so we have this system and you want to now solve it using the Gauss elimination. So what we do is that we create an augmented matrix. So our matrix, the augmented matrix, will have the A matrix, which is 3 minus 0.1 minus 0.2 0.17 minus 0.3 0.3 minus 0.2 10, and then we augment with it the B, which is 7.85 minus 19.3 71.4. Just take this last one and I'll put it in a bracket like this, and I'll say yeah. So that's the augmented matrix of A and B. Please don't change signs, don't do anything. We are just augmented them to have this matrix. Now that's the first row, second row, third row. I'll call them as R1, R2, R3. So what we are going to do now, we need to get zeros here. So we keep the diagonal as it is, and we need to have zeros here. So we'll start with the first column. We need to get zeros here. So what I'll do is I'll multiply the first row by 0.1 divided by 3 multiplied by the first row, and I'll subtract it from the second row, and whatever result I get, I'll replace it in the second row. Okay. Now when we do multiplication of a row by any number, that doesn't change the solution of our system. We can add two equations and then replace one of the equations. That doesn't change our solution. So when we are doing these row operations, our solution is not going to change. So I'm going to multiply the first row by 0.1 divided by 3. So I have my second row, which is 0.17 minus 0.3 and the number here minus 19.3, and then I have here the first row multiplied by 0.1 divided by 3. So 0.1 multiplied by 3 divided by 3 is 0.1. 0.1 multiplied by 0.1 divided by 3. So 0.1 multiplied by 0.1 divided by 3. So here I get minus 0.00333 and here I get minus 2 multiplied by 0.1 divided by 3, so that is minus 0.00666, and here I have 7.85 multiplied by 0.1 divided by 3, so this is 0.26166. Then I'll just put spaces here so that we know that what numbers are together, is to arrange the columns. We subtract this equation from this equation. So 0.1 minus this 0.1 will be a 0. 7 minus 0.0033, so that will be 7 plus, so 7 plus 0.003333, so that is 7.0033 minus 0.3 minus 0.66, so that will become plus 0.00666666, so that is minus 0.29333, and this is minus 19.3 minus 0.261666, so that's minus 19.36846. Yeah, so 19.3 no 19.561666. Okay, then what do we do with this equation? We'll just go back to our original equation and we'll replace this new equation now instead of the old equation. So here we'll get 0, here I'll get 7.00333, here I'll get minus 0.29333, and here I get minus 19.561666. so this is our system. Now we got a 0 here and we continue to get 0 down there. Just to save time with all this writing and calculation, I'm just going to take this over to Excel and show you how to do it in Excel. It will be quicker there. Okay, so we'll go back, get our original equation, try to keep it in mind. Okay, I can start here. So I had 3 minus 0.1 minus 0.2, 7.85, 0.1, 7 minus 0.3 minus 19.3, 0.3 minus 0.2, 10, 21.4. I'll just take all this, make it center aligned. Yeah, looks good. Now what I did here, I'll have the same first row here. Here now I'll have the second row minus the first row multiplied by 0.1 divided by 3. Just I'll fix these numbers because all of them we are going to multiply by the same number. So this will be a 0, and here we get the other numbers that we formed that. Now here what I do is that I'll say the third row minus the first row multiplied by this value divided by this value, and I'm going to fix them, and I copy them here, so I get a 0 here as well. Okay, and those are the numbers that I get. Just to avoid them writing them in Word takes long time, so I'm just doing it here, and also that I don't make mistakes in the calculations. Now this is my matrix now after getting rid of the values here. Sorry, I'll copy it and I'll say paste values only. Now I need to get a 0 here. Now we are done with the first column, so now what we'll do is that these two rows won't change now, just like in the first term the first row didn't change. Here now these rows will not change. We use this to get zeros here. Now we'll use this number here to get zeros below it. In the third column you use the value in the third diagonal place to get zeros below it, the fourth one the fourth column, and so on. Okay, so of course this we have to keep it 0. If I use the column here the 3, then I'm going to change this 0 here. So we do this because whatever I multiply and add 0 with 0 will remain a 0. Now the same procedure, we'll say the third row minus the second row multiplied by this number divided by this number. Should get a 0 here. Can copy it here, and I'll copy it also to the left hand side, make sure it remains 0. So now we have our eliminated matrix. We have the zeros here below the diagonal, the 3 zeros. Now we can do the back substitution. So x3 is whatever number I have here divided by the number here. So I find x3 to be 7. Now since I know x3, in this equation I have only x2 and x3, so I can find x2 as the number here minus the number here. What did I do? x2 is, I'll put a bracket, number here minus this number multiplied by x3 divided by the coefficient of x2. So it comes out to be minus 2.5. x1, now since I know x2 and x3, the only unknown is x1. So x1 is 7.85 minus this multiplied by x2 minus this multiplied by x3 divided by the coefficient of x1, so comes out to be 3. So I have my solution. X3 is 7, x2 is minus 2.5, and x1 is 3. So this is how we do the Gauss elimination method. This is called the naive Gauss elimination. This is the basic one. So this is our Gauss elimination method. This is the MATLAB code given in the book for the Gauss elimination. If we write our own code, of course it's going to be similar because it's a complicated code. You can just start from here. Before the AUG, you define the A matrix and the B matrix, and then you can just copy this code from here, and you'll get your answers. The elimination of the the efficiency of the Gauss elimination process. This slide just shows you that most of the computation goes in the forward elimination step, and not in the back substitution step. So we have to make improvements in the forward elimination steps, and this is just again to confirm this. And of course there are some modifications to the Gauss elimination process to get more efficient programs. After this we have the pivoting. I'm not going to go through pivoting. We'll just stop at the naive Gauss elimination method.